Hey Rack. Hey Pup. Today we're going to talk about finding and solving the Hadamard population conjecture. We were working on a problem called consistency, which we will discuss another time, and we wanted to know whether two specific bits were set in a vector when all we could see was the Hadamard transform of that vector. We ultimately concluded that the dot product of the fast Hadamard transform of two vectors equals the length of the two vectors times the population of the intersection of the two vectors. Let's start with some examples. Consider the bit vector called mask. It has 2 bits, and we want to know whether other vectors have those same 2 bits set. In the second and third vectors, one of the bits is missing, and in the third and fourth vectors, both bits are present. In bit space, this is easy to figure out using intersection. But if we take the fast Hadamard transforms of those vectors, then the answers are very unclear. Of course, our first step was to Google properties of Hadamard transforms. We found a few sources. Of course, Wikipedia has a page. There's a wonderful paper by Arazi, and there's a wonderful video by Gupta. But we didn't find very much, and none of it answered our questions. We spent months looking at the fast Hadamard algorithm, which is the discrete kid brother to the Fourier transform. And we looked at the fast Hadamard butterfly, which is identical to the fast Fourier butterfly. Butterflies are fractals, which is important to the consistency problem. Unfortunately, we don't really know how to manipulate fractals. Our application had 2 differences from the traditional Hadamard transform. First, we only used binary or Boolean inputs, whereas the Hadamard transform can work with any kind of input, including complex and matrix values. And second, we would use a scaling factor of 1, unlike the scaling factor of 1 over the square root of 2, which is used in quantum mechanics. After floundering for weeks, we wrote out a table of all of the fast Hadamard transforms of size 4. That is the smallest vector that produces interesting distinctions. We focused on a small question. Consider a vector with 2 bits set, in red. How can we distinguish between the vectors that have both bits set, the colored ones, and the vectors that don't, black? We eventually noticed that the dot product of the red vector with the colored vectors is always 8, and the dot product of the red vector with the black vectors is never 8. This was our eureka moment. Eventually, we conjectured that the dot product of the fast Hadamard transform of V with the fast Hadamard transform of W equals the length of the result times the population of V intersect W. We wrote more unit tests for the new equation. We tested all vectors of length 4, 8, and 16 bits, and millions of vectors of lengths 32 to 1 million, which took hours to run. We searched again online using Hadamard transform and population, but we didn't find any prior art, so we decided to try to prove it on our own. Eventually, we found the following proof. First, we'll define 3 functions. The catenate function simply appends one vector at the end of another. The population function returns the number of trues or ones in a Boolean or binary vector. And the Entwine function combines 2 vectors together in one stage of a Hadamard transform. Essentially, Entwine is the inner loop of the Hadamard transform. Entwine combines the vectors v and w to form the vector x. We could use vectors of size 1 for the base case. However, that seems unpersuasive, so we will use vectors of size 2 for this proof. We start with all vectors of size 2. Then we substitute all combinations of these vectors into the conjecture. Then we compute the fast Hadamard transforms of the vectors and the intersections of the vectors. Then we compute the dot products of the vectors and the populations of the vectors. And finally, we note that all equations reduce to true. The inductive step is based on this butterfly, which indicates the following 10 relationships. Note that vector Vn is composed of vectors An and Bn, and that vector Wn is composed of vectors Cn and Dn. A is the fast Hadamard transform of An, B is the fast Hadamard transform of Bn, C is the fast Hadamard transform of Cn, and D is the fast Hadamard transform of Dn. V is the entwine of A and B, W is the entwine of C and D, and V is the fast Hadamard transform of Vn, and W is the fast Hadamard transform of Wn. We will show that if it works for vectors of size n, then it also works for vectors of size 2n. And specifically, we will show that if it works for vectors an and cn, as well as for vectors bn and dn, then it will also work for vectors vn and wn. We start with the left side of the equation to be proved. We substitute one definition of v and w. Then we substitute a second definition of v and w. Then we spell out the meaning of entwine and dot product to enumerate the terms. Then we expand the multiplications. Then we cancel terms. Then we separate the terms into 4 groups to clarify. Then we substitute the definition of dot product for each of the 4 groups. Then we substitute the causes of A, B, C, and D. Then we apply the inductive hypothesis. Then we factor out 2n. Then we substitute the definitions of Vn and Wn to produce the right hand of the equation to be proved. It's not a big result for a mathematician, but it is a fun result for us programmers. This whole process took us nearly 6 months. This theorem seems so simple, most likely it has been done before. Alas, we don't know of any prior art. If you know of any prior work on this theorem, please add references to the comments below. Thank you.